So this composition of functions, remember compositions means we've got like a function, let's just f of x, let's just say, I think we did one of these yesterday, I won't start with it again, x squared plus 1, and let's say g of x is equal to root x, okay? When we compose these, we're going to say f of g of x or g of f of x. And it's going to be important for us to know some domains. If you remember graphing these yesterday, one of the, if I look at x squared plus 1, it might look like that. If I look at square root of x, it looks like that. And then when I compose them, one of the compositions looked kind of weird like that. It kind of looked like it was parabolic, but it got very linear on the branches of it. And then the other one looked like that, which was linear, but it wasn't the whole line, right? Okay. So one of those, the red one, ended up having a different domain than what the green one had. And I want to talk about how we arrive at those different domains, okay, and how we develop them for composite functions, okay? And the idea is, let's just start with like f of x, or sorry, f of g of x. Start with that, okay? And my hope is that we realize that this is going to be a very important function for f, okay? F's output value, the final value that we get, is dependent, it relies on what this thing does to x, right? Okay. Let's say that, I have an x value of 9. If I have an x value of 9, okay, when I plug it in there, it gives me back what? 3, okay? So x equaling 9 will end up giving, so that's an input, will give me an initial output, let's call it output sub 1, of 3, right? Okay. Now, that becomes an input sub 2, so this becomes the second input for this function f, right? And if I plug 3 in there, I get 10 back, right? If I plug that 3 into f, I get 10 back. So I started with a real number, and I got a real number back, right? Okay, and that's the concept that we want to think about with composition functions. We're running a value through two functions. Run through a function, get an output. Take that output, run through another function, get a second output, and that second output should be a real number. Okay? Well, if I do this, oh, I don't want to erase all that. Let's do this. If I do that, let's say that x is -5. Okay? So x is -5. That's my initial input. Okay? Well, let's not use -5. Let's do something a little bit easier. Let's say x is -4. Okay? Then my first output would be 2i, wouldn't it? That's not a real number, right? Okay, 2i is an imaginary number or a complex number. It's not real. Okay? So, because that's not real, am I able to plug it into f of x and get something back? No. Okay? So, that tells me for values like -4, I don't have a final output. I don't have that second output that is attached to f of g of x. So that's why my domain for this particular function, when we do this, my domain will not exist for a number like -4. Okay? So, hopefully maybe that makes some sense to us. Okay? Kind of walk through how we do this. Okay? First thing you're going to do is a couple different things you could do. Let's just go ahead and find f g of x. Okay? Let's go ahead and develop that composite function. So I'm going to rewrite this as f, and I know g of x is root x, right? So I just do that pure substitution of that function. Okay. Now I'm going to take that input and put it in here, right? For wherever I see x. So it becomes root x to go in for that spot right there. But you're going to square it and then add 1. And we're going to simplify. The root and the power cancel out, and it leaves you with x plus 1, right? Okay. So right now we know that f of g of x is equal to x plus 1. Okay. But we got to talk about the domain. Okay, because if we go back to graphing this, the domain for this linear function is only from 0 to infinity. So we're going to talk about how we find that. Okay. The first thing you do in finding the domain, first thing you do is look at your inside function and find the domain of that inside function. So find domain of, sometimes they call it the inside or input function. In this case, okay, that would be the square root of x, right? That's the inside function. I'm going to find its domain. What is its domain? Again, 0 to infinity. Okay? So what that tells us right now is that those are the only types of numbers that I can actually plug in as the first input to get my first output. Okay? Those are the only numbers that are going to give me an output that I can then plug into f. Okay? So my domain is at most that. Okay? Does that kind of make sense? When I say at most, because that's as big as the domain could be for this composite function. Okay? We could potentially start kicking extra values out from that interval. Okay? So the next thing you do is determine domain issues for f of g of x. Okay? And our f of g of x in this case was x plus 1, right? That's polynomial, correct? A very simple, basic polynomial. But are there any domain issues there? No. Okay? So what that tells us is you start with this domain, okay? And because there are no issues, you leave it as that domain. So the domain of this function, domain of f of g of x, the domain is x values from 0 to infinity after we conduct these two steps. Okay? What people struggle with is they want to compose the function and look at the final function and find its domain, which is going to be useful. But then they think that's the only thing they need to do. And they forget that there are some input values from that input function, that inside function, that are also critical to the question. Okay? So let's do, here we got time to do one. Let's do one more. Let's start with say f of x f of x is equal to 5 divided by x minus 1. And let's say g of x is equal to 4 divided by 3x minus 2. Okay, we call those rational functions. But if I just want to find f, you might see it written in your homework as f composed of g of x, but hopefully we remember that that is the same thing as f of g of x, right? Okay. So the first thing we're doing is I'm going to just create what this function looks like. Okay. So I'm going to go f g of x is 4 over 3x minus 2, right? Okay. 4 over 3x minus 2. I'm now going to take that expression and I'm going to plug it into f. Okay? And I'm going to plug it into f everywhere that I see an x, right? So in this case, it's nice to only see it once, but however many times I see x, that's how many times I got to plug that in. So the first thing's going to be, I'm going to have the 5 is going to be my numerator. But now that x becomes 4 over 3x minus 2. And that minus 1 still needs to be there. Okay, now it's ugly. We would probably eventually want to simplify this, but I think it's going to be easier for us not to simplify. Okay, at least right off the bat. Let's just go f of g of that. That's what we just found. Okay, let's talk about its domain. Okay, the first thing you have to do is find the domain of the inside function. Inside function was g of x in this case, right? So 4 over 3x minus 2. Okay, what is the domain of that function, or what is the issue in this case for this type of function? X cannot be 2/3. We cannot have division by 0, right? So Jared's taking 3x minus 2, saying that when that's equal to 0, we get 3x is equal to 2, x becomes 2/3. So we are not allowed, because of that inside function, we are not allowed to have x to be 2/3. Every other number works, right? Okay. The inside function says x cannot be 2/3. Now, the second part is to look at your composite function, which is 5 divided by 4 over 3x minus 2 minus 1. Okay? Now, this would simplify and all that kind of stuff, but that's division, right? What can this thing not be? 0. So I'm going to rewrite this as 4 over 3x minus 2 minus 1 equals 0. Okay. I'm going to add 1 to both sides. So I get 4 over 3x minus 2 equals 1. Okay. 3x minus 2 is equal to 4. All right, multiply both sides by the denominator. 3x is equal to 6. X is 2. Okay. So now I also know that I need to exclude 2. Exclude 2. Exclude 2/3. Okay. So we're going to start with the domain being all real numbers, except 2/3 and 2. I'll finish this for you guys. No.
So this becomes the interval notation that we're looking for when we kick out 2/3 and 2. Kind of giving you the graphical approach here of what this looks like. Okay, so here are the individual functions. F divided by x minus 1. Okay, and you see here that when x is equal to 1, you get, kind of have to scroll a little bit to see it, but we see that we have a vertical asymptote there, so that makes sense. And that would be kicked, x being 1 would be kicked out of the domain of that function. Here we get 2/3, so if I put in the line x equals 2/3, you see again that there's a vertical asymptote there. Okay, so that makes sense that we have division by 2/3. That would be problematic for the purple function. If we put those two together as a composite function, okay, this is what it would look like. We did that algebraically. And we see then that this is the final production. Okay. Again, if I put in x equals, in this case, 2, we get the asymptote. So we knew that 2 had to be kicked out, and that's what we saw right here. Okay. But now we also need to kick out the 2/3. But here's why. If this denominator was 0, we got 2/3, and 2/3 right here. Just think about plugging in 2/3 right there for x. You'd get 4 divided by 0. Well, you can go through and go 5 divided by, and then I get to this part, and that's an indeterminate value. So I don't know what to do with that. Can't subtract 1 from an indeterminate value. I can't take 5 divided by an indeterminate value. So 2/3 is a big deal here. All right, now I don't know why GeoGebra does this. I don't know if it's that they're showing this here, but then maybe doing some simplification behind the background in the background. Um, but they're actually, if I inspect this function, they're actually saying that 0 2/3 exists. Right there, they're saying the root, which is a 0, 0 2/3, exists. Or sorry, the 0 of 2/3 exists, or x equals 2/3 is an okay thing. If I go this way, I go 2/3. That's kind of weird how it won't accept that fraction, but if I type in 2/3 this way, it gives me back the idea that I should be getting something very, I don't know why it does that. I don't know what it's doing here. So that it kind of failed. GeoGebra, I guess, kind of fails us in this situation. But what won't fail you is your TIA 384. Okay, as long as you know how to type this function in. Okay, typing this black function in here, we have 5, and then we need to divide. Open a parenthesis. Okay, so this parenthesis here, where my cursor is now, we'll close off with that parenthesis, and that's just going to create a denominator for 5. Okay? But inside that denominator for 5, we need another fraction, so that's why I open that parenthesis and eventually close it with this one. And that will be another denominator, or give me the fraction 4 divided by 3x minus 2. And then I need these parentheses because for that 4, 3x minus 2 has a denominator. So I need to make sure that that entire 4 gets divided by 3x minus 2. If I graph this, it does look exactly the same way that this function over in GeoGebra did. Okay, so I know I've typed that in correctly. If you struggle with that kind of stuff, there are some things out there. There are some calculators online that you may be able to Google and just say like online calculator or whatever. And if you struggle seeing that this is what you want, you could ultimately type that into the online calculator and see if it spits back to you something written this way in math print. You could use GeoGebra to do that as well. I could type this into GeoGebra just as I see it on my calculator, type it in here in the input, and it should spit back something like this. I don't think it will reduce it. Some other options, if you got a newer calculator, I think if I go mode, go down to highlight math print, and then go back to y equals. I guess I didn't do it. Maybe some of your calculators might actually write it this way. All right. But regardless of that fact, once I have it in there correctly, I'm going to go to my table. And I know I should have x values that are all real numbers. Okay, so I should be able to pick anything I want to, except for the values we've kicked out. Well, we've kicked out 2/3 and 2. So I'm going to plug in 2/3. And that's verification. That error there is verification that that should not be part of my domain. You should also be able to kick out 2, hit enter, and that is also verification that 2 is not part of my domain. And I can type in any other number and I should get something back. Just type in, some obscure value, still get an output back. So these outputs getting back tell me that these were numbers that were okay for the domain because you're getting outputs. 2/3 and 2 were not okay because you weren't getting an output. Hopefully that helps. We'll continue to work with these composite functions in the next couple days. So hopefully that helps.